Hello everybody, I'm Soraya and welcome to Open Information Extraction using Wikipedia seminar. It's an overview. We'll first see the motivation, then we introduce Wikipedia-based Open Extractor. Then we will get familiar with the architecture of that, and we will see how their performance analysis, and then at the end we will decide which mode is better, shallow or deep, and at the end we have conclusion. The purpose of IE system is to extract semantic relation from natural language text. For this purpose, they use supervised learning of specific relation-specific examples. So for that, they need availability of training data, and availability of training data make problem for a large scale corpus like web and other Wikipedia and this stuff. We developed OpenIE systems for handle the unbounded number of relations in this corpus. And they use self-supervised learning. Self-supervised learning is atomic heuristics which generate label data for training. And so other issue will come up is that how well can these open systems perform. In the previous presentation, we saw the text runner, and here we will introduce Wikipedia-based Open Extractor, WOE. Its performance over precision and recall is better than text runner because it used a self-supervised learning which use Wikipedia infobox attribute values and corresponding sentences in that article. And it will operate in two modes. One is restricted to part of speech tagging, which is known as shallow features, and the other one is dependency parse features, which build a parse tree for that. We will see them in later slides. So, what is an open information extractor? It's a function from document D to a set of triples which related arg1 and arg2 related together with rel. In traditional approaches, the relation was predefined, but here we also extract relation. So the extractor should find a triple for each relation that is explicitly in the text. And here we have a sample. For example, if we have an article Stanford and we have infobox. Infoboxes are the little information box at the top left of each Wikipedia article, which have abstract information of that article. So we use the attribute of these infoboxes and their value for learning extractor. Then there is a sentence: the university was founded in 1891. So the extractor should retrieve this triple: Stanford University, established in 1891. So here is the architecture. It consists of three parts: preprocessor, matcher, and learner. In learner, we have two different modes. One is using parser feature, the other one uses shallow features, and we must select between these two, and we will see later how these two perform over each other. And at the end, we have these triples, which shows the relation between the arguments. So, in preprocessor, we have sentences splitting, which transform each Wikipedia article into HTML, then split the sentence by using of OpenNLP. And then after that, in NLP annotation, depending on which mode you are working, if you are working in the shallow feature, in the mode of shallow features, then you will use post tag and MP chunk for tagging your tokens. If you are not, if you are working in parser mode, then you will use a Stanford parser to create a dependency parse tree. Then we have compiling synonyms, because each word in Wikipedia have different synonyms. So for this purpose, we should have all of word synonyms. For that, we use redirection pages of Wikipedia and backward links. Backward links are hyperlinks which are pointing to this entity from other pages. So by using this, we will find all synonym of that word. Then in the matcher, we construct training data for the learner part. So here we have a Wikipedia page and info box. So it will go through the article and depend on the subject of the article and attribute value of the info box. It tries to find a sentence which contains all of these subject of the article, attribute value of the info box. Then it will annotate these tokens for training set. So for finding this now, we use heuristics. We have different heuristics: full match, partial match. For example, Amherst match with Amherst mask, and we use pattern of type because most of the Wikipedia's first sentence in the Wikipedia article, the first sentence is stylized. Like for example, we have in Wikipedia page for Ithaca start with the city of Ithaca is located at this. So we use this feature and recognize the type of the subject of the article. Then it uses another heuristic, the most frequent pronoun. It assumes the most frequent pronoun is the same as the initial entity we are searching. Then after matching sentence, it just returns one unique sentence. If there is several sentences, it doesn't consider that. It just considers the entities which reports just one sentence. In learner part, we work in two modes: parser feature and shallow features. In parser features, we use dependency parse trees and a pattern learner to classify whether the relation exists or not. And in shallow features, we use post tags and CRF to denote if such a relation exists or not. For example, first, if we have Dan was not born in Berkeley, then here we will see how parser features work. If we have the sentence Dan was not born in Berkeley, by using of a Stanford parser, we have this formula. Each formula shows a relation between the dependence token to the governor token, and by using this formula, we can form a directed graph. Then, if we consider the shortest path between two special tokens, for example, if we consider Dan and Berkeley, the shortest path between them called core path. But the problem with the core passes is that they're not shown all of the meaning of the sentence. Here the negation was omitted, so we will use we will have expand past. We add adjectival and adverbial tokens also for expand past. So the learner generates a core path for subject and info box attribute value, but we will use the expand path for other purpose. We first use core path, then we will see where we use expand path. We will use expand path at the end when we want to report the sentence. So first we use core path of subject and info box attribute value. Then for improving the learning performance, we have generalized core path. Generalized core path replace the words with their post tags and then reduce the post tags by replacing them with letters, like if it's noun, replace it with n, and so we call this extraction pattern. Then the WOE builds a database of patterns, these extraction patterns, for distinct patterns, and associate a frequency to each pattern, P. So for classifying, it uses a frequency for each generalized core path. If we give the WOE parse a triple for testing, then it makes its generalized core path, and it computes a frequency for that. It gives a weight for this frequency. We have f of pattern is associated frequency of the pattern, f of maximal frequency, and f of mean, it's a controlling threshold. So if the frequency of the pattern is less than the threshold, it will give the weight of 0 to that, so it wouldn't consider that pattern. Here is an example. For example, Dan was born in Berkeley. We consider Dan as arg1 and Berkeley as arg2. Then we build the core path, abstract it to extraction pattern, and then we will search through the database of pattern and extract the frequency of that pattern. Then we compute the weight for that, and then if it's more than threshold, it would return the final expression, which is the expanded path, not the core path, because the core path doesn't show all the meaning of the sentence. So what was the problem with, yes, yeah?
Can you go back to the last slide?
Yeah.
So the negation is included in the predicate?
Yeah, the negation is included. So here we have shallow features because in parser mode we reach to a high performance, but the problem is with speed. If we need higher speed for Weber scale corpora, so we come up with shallow features like post tags. For making positive examples, it used the same database of pattern as before, but for making negative examples, it would use random noun phrase pairs, which their generalized core path not be in database of patterns. And for learning algorithm, it would use a two-order CRF instead of weight. And so experiments here for examining our system, we use 3 different corpora: Wall Street Journal, from Penn Tree Bank, Wikipedia, and Web. We selected randomly 300 sentences from each of them, and then label them with 2%, and then give that to Amazon Mechanical Turk for verification. then ask people if there is positive or negative. So here we will see how these systems perform against each other. Then we see performance with respect to sentence length, extraction speed with respect to sentence length. Here we see that WOE of pose shows a better performance rather than TextRunner because it has better training data set. But WOE of parse is better under recall because it uses parser features, and parser features can show abstract relation in long sentences. That's why it's better on recall. You will see here if the sentence, if the size of the sentence increase, the F measure, F measure is the mean of recall and precision. The F measure would go down for the ones which are dependent to shallow features, but for WOE of parse is still high. So here we have extraction time. We see by increasing the sentence length, the W of parse consuming more time because it relies on parsing, and parsing would spend time for retrieving the relations which are abstract in the sentence which are long. So, which one is better, shallow or deep parsing? Shallow features like pose tags have a fast extraction over large scale corpora, but parser features by using parser trees have better training extractors, and they're very informative on abstract dependencies paths. And in the web, we have very complicated long distance relations. So parser features would be more powerful on large scale corpora like web. At the conclusion, we have WOE is self-supervised learning and lexicalized features based on heuristic match, which runs in two modes, WOE of pose and WOE of parse. In comparison, WOE of pose runs at the same speed with TextRunner, but the F measure is greater, and WOE of parse is the F measure is higher, but the time would be slower. So it would be a trade-off between time and F measure. And it's my reference, and thank you for your attention. And if you have any question, I'm here for answering.
Is the meta information in non-English language Wikipedia pages in English, or is it in other languages? Like if I looked at the info box for the German version of a given Wikipedia page.
I think they're using English medias for training. It depends on which language you're working.
I guess I was wondering if this technique could be applied to other languages.
Yeah, because if you use German articles for training, so it would work on German. It depends on other softwares, if they're working on German or English. I don't know if it's, for example, MP chunking and other stuff, if they work on German, it could apply also on German or Chinese or whatever. I think so.
Can you go back to the precision recall So at a lower recall, the shallow features are actually better, right?
Yeah, the
So-
shallow features on lower recall is better than because the relations are obvious, but if the sentence
Mhm.
length increase, the relation would be more abstract and
So if you want just few but very certain facts, you would probably just use a part of speech approach.
yeah, for the small sentences, it would be better to use W pause, but for long sentence, as we have in real world like web and this stuff, it would be better to use W parse.
Maybe any more questions? Okay, thank you again.